This whole board, all 4 sessions, and possibly even a second board, is on one theorem. Well, strictly it's called a lemma, but it's effectively a theorem. It's probably called a lemma for historical reasons. It's probably a part of a bigger theorem, bigger proof, when it was first used. And it's another version of the pumping lemma. Now, in earlier sessions, we talked about the pumping lemma for regular languages, and we used that pumping lemma, that version, the earlier version, to prove that certain languages were not regular. Okay? And this version of the pumping lemma, it's the pumping lemma for context-free languages. We will use it. First we'll prove it, and then we will use it with 3 examples. And it's only at near the very end of the 4th session of this board that we just start on the first example. And we will prove, using this version, the context-free language version of the pumping lemma, that 3 candidate languages are not context-free languages. Okay? So we're getting pretty close now to the end of chapter 2, and chapter 3 is the first chapter of a new part, a whole part. And remember, the text itself only has 3 parts. To remind you again, if you've been following me consistently, you'll know already, mentioned it several times, but other than chapter 0, which is preliminary tools, mainly math, part 1 is just 2 chapters. We're in part 1 right now. Chapter 1 was regular language, chapter 2 is context-free languages, but part 2 is computability theory. There's 4 chapters in that part. The Church-Turing thesis, decidability, reducibility, and advanced topics in computability theory. And part 3 also has 4 chapters. Part 3 is called complexity theory, and the chapters are called time complexity, space complexity, intractability, advanced topics in complexity theory. So the chapter that will follow this one, chapter 3, is the first in the part on computability, and it will introduce another kind of automaton called the Turing machine, which is able to process, recognize, if you like, an even broader class of languages. So in a sense, these first 2 chapters, first talking about regular languages and then context-free languages, and this pumping lemma that we'll do on this board will show, we'll use it to prove that there are still languages that cannot be recognized by, cannot be recognized as either, they can't be recognized as context-free languages. If a language is not context-free, then it's not a regular language, because regular languages are a subset of context-free languages. We proved that in the previous board. So we're sort of heading towards the need for more powerful types of machines, and that's the sort of lead-in to the Turing machine. And the Turing machine is amazing because it's the basis of general-purpose computers. Turing machine, as an automaton, incredibly powerful. And that's what the next chapter is all about. It's just sort of explaining its incredible power. That, I can tell you now, just give you a taste. Any computer that we have today, even the most powerful supercomputers that are processing 10 to the power 16 operations a second, which is estimated to be the human brain equivalent. So machines now have reached human brain bit processing rates. So all we have to do then is figure out how to connect up the the neurons in the appropriate way, and we will have then machines as smart as human beings who can think 1,000,000 times faster than we do, because they'll be thinking electronically rather than using chemical speed neurons. Anyway, so any machine, any supercomputer that exists today, its function, its power, if you like, is the same as that of a Turing machine. So whatever these machines, today's machines can do, a Turing machine can do. Maybe hugely less efficiently, but it still can do it, right? And that's effectively the so-called Church-Turing thesis, this basic assumption. And no one's been able to refute it so far, as far as I know. I mean, it'd be a revolution if they could. Anyway, so you can see the structure, the logic behind the structure of the book, the way it's ordered, the various parts of the book. We're heading towards the realization that there are languages that are not context-free, and we'll prove that using this pumping lemma, and hence the need for a more powerful machine. And that's the lead-in to introducing the Turing machine. And my personal favorite in the topic of computer theory is computability. You're proving things that you can compute and cannot compute, which is a mathematical proof that it is impossible to prove something, which is sort of like explains also my fascination with Gödel's stuff. And I've added a few books to my list of courses. In my original ad, I thought I would, over 30 years of the rest of my life, I would teach about 600 courses. Well, the reality is, the rate at which I'm teaching will probably make that impossible, unless perhaps things happen and maybe I'm joined by other people and they take care of the shit work, all the uploading stuff and the dumb stuff that I have to do at the moment, that takes up so many hours every day. It's really boring. It'd be nice that if I just write the board and film, that's it, and all the rest just gets done by somebody else. That would be nice. And then my productivity could go up. I mean, I could do like 2 board sessions a day, and then I could, over a lifetime, do 600 courses. But for the moment, I'm being much more selective. In fact, just recently, I made more or less a final choice of the courses I would teach in the first batch, and that batch is going to take a decade, at PhD 1 and PhD 2 levels. First year PhD, second year PhD levels, classes. And I had 1 or 2 books on the theme of Gödel and computability and that kind of thing, because it's a fascinating topic. Interestingly, in PhD 2 level, they're nearly all physics, not many math. A couple, just a handful on so-called 3 manifolds. So manifolds in 3-dimensional space, which has obvious and intimate links with string theory, and another one on knot theory. Knots and strings also intimately linked. So I take knot theory all the way up, and the other one was on groups, finite group theories, finite simple groups, a topic that absolutely fascinates me, because I have this deep suspicion, a lot of other people do as well, that sooner or later string theory or modern or near future physics, theoretical physics, will use the monster group. Now if you followed my first course that I did, the very first course in all these deGarisMPC series of courses, the very first one was an undergrad level, so junior senior, on groups, finite groups, and throughout that course I kept talking about finite simple groups, I won't say now what they are because it's a computer science course, but I'm deeply suspicious that future physics, theoretical physics, will use the monster group. That's a group with 10 to the power 53 members. That's the size of the group, and that's the largest proven largest group, because the simple groups, finite simple groups, have now been classified. That's one of the great intellectual achievements of humanity, early 1980s. So they've all been classified. We know how many there are, and we know, to a large extent, their properties. Not there yet. And the very largest one is called the monster group, for obvious reasons. It's just so huge. It's monstrous in size. 10 to the power 53 of that order. And there are already strong clues that the monster group plays a role in string theory. And since I'm more and more inclined to be a deist, I'm suspecting more and more that the universe is actually designed by some hyper-intelligent mathematician, because there are all these clues. And sometime this century, I'm the Lect guy, the Lect war guy. It seems to me eminently plausible that if humanity is going to create Lects this century, maybe at the cost of a war killing billions of human beings, but one way or another, very probably the Lects will be created, and then they become massively intelligent, and maybe they design universes. That might be one of their preoccupations, who knows. And so therefore, if that can be done this century, maybe our universe perhaps is the product of some previous Lect, call it a god if you like, or a deity, designing our universe. The rise of the Lect this century makes this idea of deism more plausible in my mind. And we have all these clues already that the universe may have been designed, like the anthropic principle. The values of the constants in the laws of physics are so fantastically, improbably, finely tuned to allow our universe to exist and for life to exist, that you're deeply suspicious. The whole thing, the whole universe, the laws of physics, they've been rigged. Now, that's not a proof. You're just suspicious that's the case. And why is the universe so mathematical? So again, you get suspicious that the universe has been designed according to mathematical principles. And so if I'm right, that the monster group in future physics plays a major role, that just reinforces the notion that our universe is